Hi guys, welcome back. We are going to start Chapter 3, Section 2 today, the structure of the nuclear atom. And we are going to continue our conversation after leaving Dalton and talking about his 5 rules of his atomic theory. And since Dalton, of course, and think of Dalton's model of the atom as being essentially like a little ball bearing. Dalton really didn't get too much past that sort of basic shape. And since Dalton, we've discovered quite a few additional particles smaller than an atom. The first of which we're going to talk about is the electron. The electron was discovered by J.J. Thomson. And J.J. Thomson was doing what a lot of scientists, and his full name was John Joseph Thomson, and he was a fairly famous British physicist. And he was doing what a lot of scientists at the time did, which was just sort of play around with cool current phenomena. It might be like electricity. Electricity kind of went through that sort of popularity where everyone's trying it out. X-rays, similarly, microwaves. Everyone's trying some different things out with this new phenomena and just sort of seeing what its properties were. Basic research at its very best. And so what Thomson was doing was he was playing around with something called cathode rays. And cathode rays were essentially a ray, a beam that was passed from one side of a glass-filled tube. The gas-filled tube had an anode and a cathode, a negative end in the cathode and a positive end in the anode. And it traveled from the cathode to the anode. And so if we take a look here at the next slide, we can see that the cathode ray tube doesn't look that different from, say, like a neon light or something like that. You've got a gas in there at very low pressure. You've got a voltage source. The beam jumps from the negative side to the positive side, and that's pretty much it. And scientists like to play around with this and see what kind of different properties it had. And with some of the experiments that Thomson ran, he discovered that these particles must have mass because they were able to move a paddle wheel, and also that they were affected by magnets. So Thomson sort of took this information, and since these beams, these cathode rays, were present regardless of what gas was in the tube, Thomson sort of surmised that everything, all matter must have these particles. So Thomson kind of thought and developed a model that would sort of incorporate these little teeny tiny particles, and he called them electrons. Teeny tiny identical negatively charged particles. He called them electrons, and there you can see a nice picture of J.J. Thomson, very serious looking fella. And also he was able to figure out the ratio of charge to mass, so he knew that they had a fairly large charge for very low mass. And Thomson established a model of the atom, a fairly popular model called the plum pudding model. And again, Thomson is taking the information that he has. I've got these little teeny tiny particles, and since they're negative, I've got to do something to account for the positive part, because the atoms themselves were neutral in charge. So what he did was he basically got a big ball of positive charge, dispersed the electrons in there fairly uniformly, and that was Thomson's model, the plum pudding model. Big ball of positive charge, little teeny tiny electrons, negative electrons, sort of embedded throughout. We don't need a lot of plum pudding today, so I like to call it the chocolate chip cookie model, which is delicious sounding. So chocolate chip cookie, plum pudding, both work. Next up, Robert Millikan. Now Millikan is going to build on Thomson's work. Millikan, another scientist, he's an American, though in 1909 he performed his most famous experiment called the oil drop experiment. And what Millikan really relied on was the use of Thomson's basically his mass to charge ratio. Thomson did a lot of work with the electron, sort of figuring out this ratio, establishing some of the basic properties, that they're negative, that they have mass, they're a particle. Millikan is actually going to be the one who determines what the charge and what the mass is, using Thomson's information, and he used sort of a simple little device. This is, I probably could go on Google and get a much better picture of the oil drop experiment, but this is what I got. I'm kind of proud of it. Basically a little atomizer, which is like a little nozzle, an aerosol nozzle, and you spray a sample of oil or something into this center container, and it drifts down, and there's a little teeny tiny hole there, and a little droplet of oil manages to fall down in between two charged plates. And what Millikan was able to do is he was able to figure out the charge on the oil droplet by altering the charge on the plates, and he was able to figure out roughly what the charge of a electron was by looking at the charge on the plates, because when these droplets got blown into the container here and they drifted down, electrons were ripped away. And so Millikan was able to use this information to establish the charge, and because he had the ratio from Thomson, he was also able to get the mass. And again, it's very important to note that Millikan did use Thomson's information and was sort of riding on his research. And because the mass that Millikan came up with, I think, do we have that on there? Maybe that was the previous one. Because the mass that Millikan came up with for the electron was so small, scientists kind of looked at this data and said, well, there's got to be something donating mass, because the mass of this electron accounts for a very, very, very small percentage of the mass of the overall atom. So what else is in there that's contributing mass? So more data opens more questions, which is kind of how science works. The next scientist we're going to talk about is Ernest Rutherford. And Ernest Rutherford was a pretty cool guy. I think he was a New Zealander, if I'm not mistaken, but he did a lot of his work in Britain, in England. But Rutherford is credited with discovering the nucleus, and Rutherford was another one of these scientists who was interested in everything. He was very interested in X-rays. They were discovered around the time that he was really getting into science, and also is interested in these particles called alpha particles. And alpha particles are basically stripped down helium nuclei. It's like the nuclei of a helium atom with no electrons around it. But again, Rutherford didn't know that. He just knew they were high energy and lots of fun. And so Rutherford's most famous experiment is something called the gold foil experiment, and this was performed in 1911. And basically what Rutherford did, solid mustache, is he fired a beam of particles at a thin piece of gold foil, and what Rutherford essentially expected to have happen was for these particles to hit, kind of plinko their way through, like bounce around, like tick, 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 off all the atoms that were in there. Because again, we're still operating kind of off this idea that atoms are kind of a solid sphere. And so he thought they'd kind of bust their way through like a fullback going through the line and kind of stagger out the other side, sort of like a spray, like spraying around. And then he had some film. I think it was like a zinc sulfide film or something like that, to pick up the alpha particles so he could see what the distribution was like. So his expectation was most of this stuff is going to pass through at some slight angles, but nothing crazy. What happened was that the beam hit the gold foil and then went all over the place, with the vast majority of particles passing straight through almost unimpeded. Again, this is a very, very thin piece of gold foil, and these alpha particles are very, very high energy particles. And some of the particles even bounce straight back. So Rutherford's hypothesis was that the alpha particles would deflect like spray from a nozzle, so slight angular change. And what happened was that the majority of the particles passed straight through, with a small percentage bouncing straight back or being widely deflected, like we said. And this was super surprising for Rutherford. Like, I mean, he was giddy with excitement over this result because it was totally unexpected. He thought these alpha particles are so high energy that they were going to kind of like bam their way through, and they didn't. Some of them hit and bounced straight back. Now the majority went right on through, and this kind of gave Rutherford some pause. Okay, since most of the particles passed straight through, Rutherford thought, well, that must mean they didn't hit anything. So most of this atom must be empty space, right? If there's nothing getting in the way, that just must be empty space. So these alpha particles, which are really tiny, just kind of shoot on through and nothing gets in their way. And since a few particles bounce back, there must be something in there that's super heavy, super dense. If you look at a helium nuclei compared to a gold nuclei, the gold nuclei is many, many times more massive. So it would make sense that the alpha particle would hit that gold nuclei like a ping pong ball bouncing off a bowling ball and come firing straight back. Again, only a very small percentage of the alpha particles did this, so this nuclei, or this, see, I'm giving it away, this region of the atom must be very, very dense. And it must also be positive because the alpha particles were positive. And if this super dense region were negative, the alpha particle would have hit it and stuck. But it didn't do that. So this is sort of what happened. And you can see here that we've dramatically increased the size of the nucleus. In fact, the nucleus is so small that if an atom were a football field, the nucleus would really be like a baseball sitting on the 50-yard line or something like that. The nucleus is a ridiculously small amount of the volume of an atom, but a tremendously large amount of the mass. It's really kind of mind-blowing. And so we can see most of the particles passed right on through. Okay, but very few were that were right on track, hit that nucleus and either bounced straight back or deflected off. So this tiny, massive, positively charged region was called the nucleus. It was later found to contain protons and neutrons, and it has a density of about 2 × 10⁸ metric tons per centimeter cubed. Think about that. 2 × 10⁸ metric tons per centimeter cubed is the density. That is some dense space right there, or material. So protons, same size charge as electrons, but opposite in sign. And they're about 1,836 times more massive than an electron, or 1.675 × 10⁻27 kilograms. So they're massive compared to an electron, but not very massive compared to just about anything else. And again, these were established by Rutherford. The other particle was the neutron, discovered by James Chadwick a little bit later. And they have a mass virtually identical to that of a proton. I think I was going to type something else in there, what the exact charge was. They're a little heavier. Okay, so they're a little heavier. You may want to jot that down somewhere, but they are neutral in charge. And the nucleus is held together by a very powerful force called the strong nuclear force. And it operates over a very short range, but it's very, very, very strong. So when that force is broken, such as in a nuclear reaction, the energy given off is fairly significant. Now this nuclear force is only good to a point. For example, anything past 83 protons in the nucleus starts to become unstable. And what do we call that when a nucleus is unstable? We say that that nucleus is radioactive. So when something is radioactive, it's typically because they have more protons and neutrons in the nucleus than what these nuclear forces can keep together. And after that, like we said, it breaks up. So Rutherford's model had 2 parts. Again, Rutherford's model is a change from Thomson's model, which is a change from Dalton's model. But Rutherford's model had 2 parts, the nucleus and the electron cloud. And the electron cloud is sort of that charged cloud around the nucleus. Think of it like a swarm of gnats, right? like these electrons are just kind of buzzing around, and that's what Rutherford kind of imagined, these electrons out there floating around the nucleus, providing most of the volume, almost none of the mass. And the cloud is still super small. It's just measured in picometers. So almost no mass, but virtually all the volume. And that is going to pretty much wrap things up